All right, so now for moving on to the last type of equation, is called Bernoulli equations. So the Bernoulli equation is the equations of the form dy dx plus p of x times y equal to q of x times y to the power n, where p of x and q of x are continuous functions. On the interval from a to b, just some interval, and n is a real number. Right, so this equation is called a Bernoulli equation. Okay, so I mentioned earlier that this equation looked very much the same with the one where you can use a integrating factor method. Right? So if you notice that, you also need to notice that n when n equal to 0 and when n equal to 1. Right? So notice that when n equal to 0, you have dy dx plus px times y equal to q of x. You can just use integrating factor. Right. Now, when n equal to 1, you have dy dx plus px times y equal to q of x times y. Then you can combine these two terms together, and then you can use separations of variable technique to solve the solutions. Okay. So that's the case for the Bernoulli equations. Now for the procedure, that is in the case of n greater than or equal to 2. Okay, because again, when n equal to 0, you can just use integrating factor. When n equal to 1, you can just use separations of variables. Now in the case of n is greater than or equal to 0, sorry, when n is greater than or equal to 2, the differential equations, again, is of the form dy dx plus px times y equal to q of x times y to the power n. Now, what you do is that you divide both sides of these equations by y to the power n. Right? So that is, you have 1 over y to the power n times dy dx plus p of x times 1 over y to the power n minus 1 equal to q of x. Okay. Now, the next step is for you to use an exponential law, or law of exponent. Law of exponential. Wait, law of exponent? Law of exponent. You need to know that, right? So law of exponents. So y to the power n is in the denominator. So there's the phrase say that when you cross the line, you change the sign. Right? That is y over n, so y to the power n in the denominator. When you bring that up to the numerator, you change the sign of the power. That is y to the power negative n times dy dx plus p of x times y to the power negative of n minus 1 equal to q of x. I need to simplify this a little bit so that I have y to the power negative n times dy dx plus y to the power 1 minus n times p of x equal to q of x. Okay. Now, after this manipulations, what you do is you substitute u equal to y to the power n minus 1 minus n. And then you can derive by du dx. Then du dx is equal to d dx of y to the power n minus 1 minus n. So the derivative of this gives you 1 minus n times y to the power 1 minus n minus 1 times dy dx. Because you need to use the chain rule. Derivative of the outside function multiplied with derivative of the inside functions. and then du dx equal to 1 over n times y to the power negative n times dy dx. But let me continue with this. But what do you see here? If you divide both sides for 1 minus n, you have 1 over 1 minus n du dx equal to y to the power negative n dy dx. And then you utilize these equations again. Okay, so y to the power negative n dy dx is equal to q of x minus this term. Okay, but from, so q of x time minus p of x times y to the 1 minus n, you get what? So you substitute y to the power 1 minus n as u. You have q of x minus p of x times u. Then du dx, so 1 over 1 minus n du dx is du dx is equal to q of x minus p of x times u. Okay, manipulate this further. You have 1 over 1 minus n du dx plus px times u equal to q of x. Okay, and since this one is a constant, this equation can be solved using a integrating factor. Okay, so there's a lot to unpack here. It's a long procedure, but when you actually get into an example, it's not going to be too bad. Right? It's just that you have to be able to identify that this the differential equation you're working with is the Bernoulli equations, and then follow the procedure. So this related to the Bernoulli equations. That is, so the Bernoulli equation is dy dx plus p of x y equal to q of x times y to the power n. In this case, you have p of x going to be equal to -5, and q of x is equal to -5 over 2 times x. Okay, and y to the power n, therefore n is equal to 3 in this case. So there's a few things that you can do now is to identify p of x is equal to -5, q of x is equal to -5 over 2 times x, and n is equal to 3. Okay. Now for this equation, what we're going to do is divide both sides of the differential equation by y cubed. Right? I'm just following the procedure that we see earlier. Right? When you identify y to the power n, divide both sides for that. Okay. So divide both sides of the differential equations by y cubed. We get that y 1 over y cubed dy dx minus 5 times y over y cubed equal to -5 over 2 times x. Okay. Now let's simplify this a little bit. So y over y cubed is equal to 1 over y squared. Let's do 1 over y cubed times dy dx. Next term is 5 times 1 over y squared equal to -5 over 2x. The next step is for substitutions. So what we're going to substitute, so go back to the procedure here, that you have, you use substitution u equal to y to the power 1 minus n. Okay, what you do is that, take this term right here, always going to be for the middle term, right? And that is going to be your substitution. So you let u equal to 1 over y squared, or this is y to the -2. Then you have du dx going to be equal to, So find the derivative of this term. It's going to be -2 times y to -3 times dy dx. So any questions on this step? You know where this term coming from? Okay, let me know if you don't get it. Right. So basically this is from the derivative of y to the -2. Take the derivative of that, you have -2 times y to the -2 minus 1. So that's why you have -3. And then this is chain rule. Right? So you take the derivative of the outside function, then multiply with the derivative of the inside function. So that's what you got. So far, so good. Or this is equal to -2 times 1 over y cubed times dy dx. So this term right here match with the first term in the equations. Okay. So you can see that 1 over y cubed dy dx is equal to -1/2 times du dx. Then you get that. So you replace this first term in the original differential equations by the new variable, right? By the new derivative. Then the differential equation becomes at -1/2 du dx minus 5 times 1 over y squared, but 1 over y squared is equal to u already. So it's 1 over u, sorry, it's times u, and equal to -5 over 2x. Then you simplify further by multiply both sides of this equations by -2. So by doing so, you get du dx plus 10u equal to 5x. And this is the transform equations. Okay. Now for this transform equation, you can use, so the dependent variable is u and the independent variable is x. With the setup, you can use integrating factor to solve the solutions. So let me follow through with that. So we use the integrating factor to solve the transform differential equations. So that is, you introduce an integrating factor, mu, right? So in this case, the mu of x is equal to e raised to the power p of x dx, for p of x is equal to 10 in this case. So this is p of x. And this is q of x, okay, for the transform differential equations. And you have e to the integral of 10 dx equal to e to the power of 10x. Okay. Again, for integrating factor, this is the only place in most of mathematics, physics, and engineering where you don't have to use the plus c for the indefinite integral. Okay, so I'm going to skip the plus c for this term. Now, the next step is to multiply this integrating factor on both sides of the transform equations. Then, you have that e to the power 10x times du dx plus e to the 10x times 10 times u equal to e to the 10x times 5x. Okay, so the right-hand side, sorry, the left-hand side going to be always the derivative, right, of the product between the integrating factor and the dependent variable. So in this case, e to the 10x times u. Then this is equal to 5x times e to the 10x. Any question on this step?
Yeah, could you repeat the first thing that you said, like that the left-hand side is always going to be the derivative of the...
So, okay, so the left-hand side is always going to be the derivative of the product between integrating factor and dependent variable. Always, always. Okay. So the product of integrating factor and this one is dependent variable.
Thank you.
Yep. The right-hand side remains the same, it's just we write differently, but all the terms are there. Any other questions on this step?
No.
Okay. Now the next step is to integrate both sides of this equations. You get that e to the 10x times u. So you integrate both sides of the equation with respect to x. So let me clear that out. So then integrate both sides of the equation with respect to x. And therefore you have the left hand side going to be e to the 10x times u equal to 5x times e to the 10x dx. The right hand side, you can use integration by parts to solve the solutions. I'm going to pull out the 5 for now. All right. So you let, so it's going to be confusing. So let, all right, so let me use another letter here. So because we already have u, so just avoid confusions, I'm going to use z. Let z equal to x. Therefore, dz equal to dx. And v is equal to, or dv is equal to e to the 10x dx. Or v is equal to 1 over 10 times e to the 10x. Okay, so instead of u, I use z just to avoid confusions. Then you have that. The left-hand side remains the same, so e to the 10x times u. But on the right-hand side, I have z times v, which is 1 over 10 times x times e to the 10x, minus the integral of v dz in this case, so 1 over 10 times e to the 10x dx. Okay. Now you have one more integral to tackle. So you have the integral of this e to the 10x. You can pull out the 1 over 10. So 5 times 1 over 10 x times e to the 10x minus 1 over 10 times another 1 over 10 times e to the 10x. This is where you have the plus c at the end. Now if you divided both sides for e to the 10x, you obtain u. So u is equal to 5 over e to the 10x. 1 over 10 times x times e to the 10x minus 1 over 100 times e to the 10x plus constant c. Okay. Now what is u, right? So this we move to the last step of the equation, that is of the process. That is, you're going to turn, let me use the procedure here. So you're going to express the solutions in terms of the original variables. So this is the last step that we're going to use. That is to express the solutions in terms of the original variables. So in this case, u is equal to 1 over y squared. Okay. So this is 1 over y squared equal to 5 times e to the 10x. Okay, so that is the general solutions to the differential equations. You may wonder why I don't simplify at all. Right? You can technically simplify, distribute this term into the brackets, and then simplify the expressions a little bit further. But I want you to focus on doing the procedure and obtain the solutions that way. Okay. Now, if you submit the questions or the answer and just leave it like this, it's totally fine with me. It's totally fine with me. But of course, if you want to go further a little bit, then it's totally fine with me as well. So let's do that. So I distribute this term into the brackets, and I get 1 over y squared equal to 1/2 times x minus 1 over 20 times just 1 over 20 plus 5 times c times 1 over e to the 10x. So this is a little bit redundant, right? So 5 is obviously a constant, c is a constant, so you can combine them together to get a new constant. This is 1 over y squared equal to 1/2 x minus 1 over 20 plus capital A. And instead of 1 over e to the power 10x, I'm going to do e to the negative 10x. Okay, so that's it for the Bernoulli equations for this particular problem, this particular example. I know there's a lot involved here in these questions. If I give you one problem like this in the test, it's good, right? Because you have to use
Maybe.
a lot of knowledge into solving this one problem, right? The knowledge of substitution in transformations, right? Because you have to use the correct substitution, otherwise the problem not going to work. You need to know how to use integrating factor, right, to solve the solutions. And of course, you need to use integration by parts, right, to solve for the integral, and then combine everything together to get the general solutions. And I can obviously make the problem a little bit longer if I give you the initial conditions, so that you can use to find the solutions or the value of capital A for the particular solution. All right, this is a long problem. Let me know if you have any questions.
No questions.
No questions. Okay. I'm gonna let that sink in for another 30 seconds.
And these integrals are pretty much unsolvable if you don't choose the correct substitution, right? So you should know pretty quickly whether or not you've made a mistake.
Right. And you cannot even use, right, if you're thinking about using integrating factor directly, then it's not really fall in the form that you can do that. And like you say, eventually you will run into the problem that you cannot even evaluate the integral. It's also true for the case of separations of variable, and obviously it's not going to work for exact differential equations at all. If you follow through with that originally, right, without doing substitutions, you will get something, but it's not correct something that you want to have. Okay, now let me going to do the last problem here for substitution in transformations. Any questions? Any questions? All right, so solve x times dy dx plus y equal to x squared times y squared. Again, I want to bring up the Bernoulli equations, that is dy dx plus p of x times y equal to q of x times y to the power n. Right. So that is, you need to turn your differential equation in this form, that is dy dx multiplied with 1 only. So we still have x in front of dy dx. Therefore, the first step is to divide it both sides by x. Okay, and you get dy dx plus 1 over x times y equal to x times y squared. Right. So in this case, p of x is equal to 1 over x, q of x is equal to x, and n is equal to 2 in this case. Now you identify that the y squared is going to be the term that you have to divide both sides for. So divide it both sides of the differential equations by y squared. We get that 1 over y squared times dy dx plus 1 over x times y over y squared equal to x squared. And then you've simplified the middle term. 1 over y squared times dy dx plus 1 over x times 1 over y equal to x squared. And the substitutions is going to be this 1 over y. So substitute on left. let u equal to 1 over y. And therefore du dx is going to be negative 1 over y squared dy dx. Or 1 over y squared dy dx is equal to negative du dx. So you substitute u by 1, you substitute 1 over y by u, and then from there 1 over y squared times dy dx by negative du dx. Okay. Then you have that. So this term now becomes negative du dx plus 1 over x times u equal to x squared. Now this is similar to the form where you can use integrating factor, but a few things here that you need to consider. That first, multiply both sides of these equations by negative 1. You have du dx minus 1 over x times u equal to negative x squared, and this is the transformed equations. Again, from here you can use integrating factor to solve the solutions. So we use integrating factor to solve for transform equations. That is, you introduce an integrating factor mu of x equal to e to the power p of x dx, for p of x is equal to negative 1 over x in this context. So e to the power negative 1 over x dx. This is equal to e to the negative ln of absolute value of x. Okay. Now the negative ln of absolute value of x, you bring that into become power. You have e to the ln absolute value of x to negative 1. Okay, and e and ln cancel out. And you're left with absolute value of x raised to the negative 1. Okay. So in this case, you have an absolute value, but bear with me here. Okay. You're going to drop the absolute value. I'm going to explain in a minute why that is the case. Okay. Now what you do is that you're going to multiply this integrating factor on both sides of the transform equations. You get, so multiply both sides of the transform differential equations by mu of x equal to x to the negative 1. We get that x to the negative 1 times du dx minus x to the negative 1 times 1 over x u equal to negative x to the negative 1 times x squared. Okay. So why we can drop the absolute value? You see that we have to multiply both sides of the differential equations by the integrating factor. So that is, you're going to have absolute value. You're going to have absolute value. You're going to have absolute value here. But then when you drop the absolute value, that means you have plus and minus solutions. Okay. But because this happens simultaneously on both sides of the equations, the plus and minus kind of cancel out. And therefore, it's a little bit redundant that you have to use the absolute value, or you have to carry the absolute value for the integrating factor. Because eventually, at this step, the absolute value or the plus and minus have to be canceled out. You with me on that? And therefore, it's not necessary to carry the absolute value from the integrating factor to the transform differential equation or to the differential equation at all. And you can use the similar argument for the case where you have the plus c, right? Here, again, the integrating factor, use the indefinite integral, but you don't need the plus c. Why? Because when you multiply both sides of the differential equation by the integrating factor, you have the plus c on both sides of the equation, so they all cancel out. And because of that, you don't need to have the plus c for the integrating factor. All right. So here I'm going to simplify this. the left-hand side is always going to be d dx of the product between the integrating factor and the dependent variable. The right-hand side, you simplify, you left with negative x. Any questions on this step?
No.
I may make a mistake somewhere here. Okay, so bear with me here. Let me walk you through this one more time. So you have the differential equation. Okay. It's not in the form that we're looking for. So you have to turn that into the form of the Bernoulli equations by dividing both sides for x. And therefore, you get that p of x is equal to 1 over x, q of x is equal to x, and n is equal to 2. That is, you're going to divide both sides of the equations by y squared. And this is what you got. So the mistake is here. It's not really a mistake yet, but we've been using the right-hand side to be x squared, but it's not x squared, right? So from this equation, you have only x. So q of x is only equal to x. So I apologize for that. So let me turn that into x here. So this is x. Everything is fine up to this point. So this is x. And this is -1. So everything is correct now. So that's the only mistake, is that we keep writing x squared on the right-hand side instead of x. Now at this step, you get it? You follow my argument there? You see the mistake I made? Yeah. Okay. So now you integrate both sides with respect to x. And we got that x -1 times u equal to the integral of -1 dx, or this is just -x plus c. Yeah. So x to -1, that is 1 over x. So 1 over x times u equal to -x plus c. Multiply x across, you have u equal to -x squared plus cx, c times x. But u is equal to 1 over y. Then you have 1 over y equal to -x squared plus c times x. So this is the general solutions. And for this general solutions, again, you can just leave it like this, or you can flip the solutions over, so you have y equal to a fraction. Or you can write y equal to 1 over -x squared plus c times x. So you have two different forms here. So this is general solutions. In an implicit form. And this one is the general solution in an explicit form. Okay. So that's it for Bernoulli equation for substitution and transformations. I know there's a lot of steps involved in one problem, but if you go through the example one more time, you will see all of this type of procedure are very repetitive. If you quite understand where you have to do divisions, where you make the substitutions, everything else could be okay, right? Especially at the beginning. If you know how to make the substitution or what to do substitution for, then everything else will follow.